I was trying to predict something for a marketing campaign recently, and I had this classic problem. I was just drowning in data,
Oh, right.
but I was completely starved for any real insight. And it made me think about that fundamental struggle. Doesn't matter if you're predicting weather or anything else. How much useful knowledge is actually in what you're observing?
That is the essential hurdle, isn't it? Both in philosophy and just practically in science. You need a way to mathematically quantify that information density, the quality of knowledge in a measurement.
Okay, so let's unpack this.
Yeah.
Because the answer, it turns out, is this amazing statistical tool called Fisher information, or FI.
Pioneered by the great Sir Ronald Fisher. It's a metric that measures exactly how much information an observable random variable, let's call it x, carries about some unknown parameter you care about, theta.
And that's our mission for this deep dive. We're going to get into what this metric is, why it's so important, and how it really sets the absolute limits on precision and everything.
In pretty much every field that uses data, yeah.
So instead of jumping into heavy calculus, can we think about this visually? Is the core idea that Fisher information measures how sensitive our likelihood is to tiny changes in that parameter we're trying to guess?
That is the perfect way to get an intuition for it. Yes.
Yeah.
We often visualize FI by looking at the curvature of the log likelihood function.
The curvature, okay, so the shape of the graph.
Exactly. If you have high Fisher information, that function is super sharply peaked.
Like a steep, pointy mountain.
A very steep peak. And that steepness tells you that if you just shift the parameter a tiny bit, the likelihood of seeing your data drops off a cliff.
So the data is basically screaming the correct value at you. It's high information.
Precisely. And the opposite is true, too. If that curve is really flat and spread out, a blunt maximum, then your FI is low. You'd need tons and tons of data just to narrow down the true value.
That's such an elegant idea. A sharp curve means strong evidence. A flat curve means you're dealing with ambiguity.
And this quality, this information quality, it scales beautifully. FI has this crucial property called additivity.
Meaning if you do more experiments.
Right. If you take, say, independent observations, the total Fisher information is just n times the information you got from one. The knowledge just adds up, nice and clean.
So now we have a number, the FI value, that tells us the quality of our knowledge. What does that actually buy us? How does it help us predict the real parameter?
It buys us a limit, a hard limit. And this is where Fisher's work becomes really a fundamental law of estimation. It's called the Cramér bound.
The Cramér bound.
Correct. What it says is that the inverse of the Fisher information, so 1 divided by the FI, gives you a lower bound on the variance or the imprecision of any good estimator.
So you literally can't do better than that.
You can't. High FI means high precision is at least theoretically possible. It sets the speed limit for how accurately you can ever hope to estimate that parameter.
Which means FI is also a tool for design. Right?
Yeah.
If you want to design a better experiment, you're really just trying to maximize the Fisher information from the start.
Yeah. That's optimal experimental design in a nutshell. And we see the payoff of that thinking everywhere today. In machine learning, for instance, FI is using techniques to stop neural networks from forgetting old tasks when they learn new ones. It helps protect the most important connections.
That focus on finding what's most impactful, the most valuable information, that actually reminds me of our sponsor, Embersilk.
Ah, right.
Yeah, because if you're looking at AI, training, automation, or integration, and you need to figure out where those agents can make the biggest impact for your business, that kind of efficient design is everything.
It absolutely is.
You can check them out at embersilk.com for your AI needs.
And the reach of FI, it goes even further. It defines physical limits on our own perception. In neuroscience, it provides bounds on the accuracy of neural codes. It was even used to derive what are called McAdam ellipses.
What are those?
They define the absolute limits of human color discrimination, the smallest possible change in color that we can detect. FI literally maps out the boundaries of our own senses.
So it defines limits for machines, for experiments, and even for our own biology. Does this connect back to the fundamental mathematics of information itself?
It does. It connects through a concept called relative entropy, or KL divergence, which measures how different one probability distribution is from another. The amazing thing is that Fisher information represents the curvature of that difference.
So geometry is tied directly to information.
It is. Which brings us to a final, pretty profound thought to leave you with. The framework of Fisher information actually defines what's called a Riemannian metric. It transforms this abstract space of parameters into a geometric manifold, a surface with shape and distance.
Wow. So our statistical knowledge fundamentally has a hidden, measurable shape.
It's an inspiring thought, isn't it? That the act of discovery isn't just calculation, it's a form of geometric exploration, guided by the mathematics of information.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.